It's a general definition, no matter how complicated it is. So let's look at non-linear function. Now it's obvious a linear function we've exhausted. This is the end of it. There's nothing more in it. But in a non-linear function, here's your 45-degree line. Suppose this was your function. Then it's immediately clear that this is a stable fixed point because the slope is less than 1, and this is an unstable fixed point. So if you start at any point here, you're going to flow off to minus infinity. If you start at any point here, you're going to flow into this, and if you start in between also, you flow in there, because if you do this, you go here, and you pick this. Now you could have more complicated possibilities. You could have stability from one side, instability from the other side. That's again a marginal fixed point. So suppose you have this guy here, and you have a curve which comes along and touches it and goes off. Then you can see that as you go from this direction, the slope is tending to 1 from smaller values, and here it's tending to 1 from larger values in magnitude. So if you start here, you will flow in, but if you start there, you will flow out. So this has slope exactly equal to 1, but it is stable from one direction, unstable from another direction. So I would say it's unstable in any case, because it's not coming back from all directions. But it's a marginal fixed point. Now, we would like to restrict ourselves to finite regions of phase space. So I need a function which is defined in a finite interval and which is non-linear in this finite interval, and which displays all kinds of strange properties, such as fixed points, higher order fixed points, cyclic points, etc., as well as exponential separation. And the simplest of these was discovered long ago by people playing with pocket calculators. It was certainly known to people even before that. It was certainly known to von Neumann and Coulomb because they used this. And this is called the Wright-Bernoulli shift. I'd like to call it the Bernoulli map of the unit interval. So the unit interval is, and the rule is simplicity itself. It's xn equal to 2xn minus 1 modulo. It says, take any number between 0 and 1, double it. If the number is greater than 1, throw away the integer, keep the fraction, and keep units forever. That's the rule. Now what's happening here? What's the map look like? Oh, by the way, this innocuous looking thing is a C system. It's way beyond what you normally would see. It's globally exponentially unstable, and it is as random as a coin toss already. So although it looks like an artificially constructed example, it will illustrate all that we want. Yeah. I haven't said why it's as random as a coin toss. I will say so explicitly. After we study the properties of this map, you will see in what sense it is exactly as random as a coin toss. But first, let's look at this map. What's the shape of this map? Basically, I have 0 to 1. Here's xn minus 1, and here's xn for any n, because it's a function, right? It says twice as much. So it says draw, this is 1, draw line of slope 2, and the moment it exceeds 1, you cut it and put it back here by subtracting 1. So this is a discontinuous map. That's the map. 2 straight line segments, each of which has slope 2, and at x equal to half, there's a discontinuity in the map, finite jump. Now we ask, what happens to points under this iteration? Well, first of all, what are the fixed points of this map? The fixed points are wherever this 45-degree line hits the map. And that's happening at 0 and 1. What's the slope at 0? Well, the slope of this graph is always 2. 2xn, it's always 2. Right? We can write this analytically. This is equal to 2xn, 0 less than equal to xn minus 1, minus 1 less than half, and 2xn minus 1 minus 1 for half less than equal less than xn minus 1 less than equal. At half there is a discontinuity. So we have a formula for it. We have both these graphs here. Now the fixed points are at 0 and 1 and the slope is 2 in magnitude at each point. So they're both unstable. Now you could say, oh, doesn't matter if the fixed points are unstable, maybe this is what happens to an initial point. I start with some initial point x0, let's say some initial point A, that goes to some point B. This is equal to f of A, and that goes to an initial or some other point C, which is equal to f of B, but perhaps this C is A itself. So A goes to B, B comes back to A, which then goes to B, which comes back to A. What would you call this sort of system? This kind of initial point? It's part of periodic motion, except it's not a periodic trajectory, but a periodic orbit, or a periodic cycle. So you immediately say, oh, there's a possibility of periodic cycles. Period 2. Can we have such period cycles here? We have unstable fixed points, which are period 1. A fixed point is after all period 1. It says it goes to itself. Can you have period 2 points? How would you discover period 2 points? You iterate this function, because you're saying f of x must be equal to x. But it should not be a solution of x equal to f of x. So do it graphically. Let's do the thing graphically. So f2 of x versus x. So iterate this function once and then write down this function. Always modulo 1. So if I iterate 2x, it becomes 2x times 2, which is 4x, but modulo 1. So what I have to do is to draw a straight line of slope 4 and cut off all the integer portions and bring it back and stick it down. So that's f2. This is half. That's a quarter. That's 3/4. That's my map, f2 of x. And now I ask, what are the fixed points of this map? There are 4 fixed points now. There's 0, there's 1, and there are these two new guys. That's a period 2 cycle. That means under iteration, this point will go there, that point will come back here. What points are these? What values are these? Yeah, 1/3. 1/3 and 2/3. Because 1/3 goes to 2/3, which is then doubled to 4/3, but you remove the 1, it comes back to 1. So it click-clocks between 1/3 and 2/3. That's a period 2 cycle. Is it stable? Maybe the fixed point is unstable. Maybe the period 2 cycle is stable. Is it stable? No, because the slope is greater than 1. There's no way this is going to happen. For a period 2 cycle to be stable, the magnitude of the slope, product of the slopes at both the points of this orbit must be less than, and each of them is 2, so it's not stable. What about the next one? You could have period 3 cycle, period 4, period 8, and so on. What about those things? You see, every time you iterate the map, the slope is getting worse. So all periodic orbits in this map are unstable. Then the question is, which points lie on these periodic orbits? What's the measure of these points? What's the measure of the fellows who don't lie on the periodic orbit, and what happens to them eventually? The short answer is that all rational points will be part of periodic orbits, as we'll see in a second. All irrational points will not lie on periodic orbits, and they have a measure or total length equal to 1. Because the rational numbers are dense in the real number, in the real interval, but they form a set of measure 0. The length is 0, total length is 0. Now how do we do that? How do we see that easily and cheaply? In this problem you can, because all you have to recognize is that you can always write this number x0 as equal to 0 point, write it as a decimal in binary in terms of zeros and ones. So you can certainly write it always as 0 point A0, A1, A2, A3, all that. If it's a rational number, this will end at some point, or right, or start recurring. If it's an irrational number, it will not recur and will go on forever. The symbol of zeros and ones. So each AI. So 0 point something something. All that. What's x1 equal? It's twice x0, but since we've written it in a binary decimal notation, this actually stands for 2 to the, it stands for A0 over 2 plus A1 over 2 squared plus A2 over 2 cubed plus 1. That's what this number stands for. Right. Now you're multiplying it by 2, which means that you're moving everything by 1 decimal place to this side, and therefore this becomes A0 dot A1, A2, A3. What could you conclude if A0 is 1? If A0 is 1, you will conclude that x0 was bigger than half. Right? If A0 was 0, you conclude that x0 was less than half. If it's less than half and you double it, it's still in the interval. But if it's bigger than half, you have to subtract the 1, which is equivalent to removing the A0. So this is gone. It is 0 point. Whether A0 was 0 or 1, you still have to remove it. That is equivalent to saying that if you give me an xn minus 1, I can find an xn uniquely. But if you give me an xn, I don't know whether it came from here or here. I've lost that information. And if I iterate a second time, there could have been 4 places from which it came. I iterate a third time, 8 places. So each time you're losing information. Or yet another way of saying it is, if due to the finiteness of the human condition, I stop at the millionth decimal place here and then put zeros everywhere else because I'm a finite person, then after a million iterations, that error has come to the first decimal place and I'm finished. After that I get nonsense. So this map already demonstrates loss of information and chaos in this sense. That any initial error amplifies. And it amplifies with 1 bit at a time in every iteration. By the way, because of this property, that all that you're doing is deleting this and moving the decimal point 1 place to the right, it's also called the right Bernoulli shift. And mathematicians who study ergodic theory are very fond of shifts. They're always defining infinite symbol sequences and shifts on them, right shifts and left shifts and so on. There's a huge amount of literature on this. They know a great deal about it. This particular thing is some kind of paradigm. It's this Bernoulli shift is like the Wiener process. It's like mathematical Brownian motion in stochastic processes. In some sense, all classes of stochastic processes can be, with reparameterization of spatial and time variables, be converted to Brownian motion. In the same sense, many things can be converted to Bernoulli shift. Now, what are the periodic points? What would they look like? Well, you can see that all the rational numbers will be periodic. Take 1/3 for example. What's 1/3 equal to? In this notation? It's certainly less than half, so it's 0. It's certainly greater than 1/4, so it's 1. Right? And then there's a 0, and then there's a 1. That's 1/3. And what's 2/3? It's just. So it's clear that under the Bernoulli shift, this goes into that goes into this, and it just simply recursive. What about 1/5? So you can see it's part of a period 4 set. And that will have a decimal expansion in which a pattern of 4 digits will go on repeating these things. Every rational number is part of a periodic set. Every rational number is unstable. And every number in between rational numbers, namely all the irrational numbers, they get thrown out on both sides. You see, after all, where is this loss of thing coming from? It's coming from the fact that if you had a saddle point and you have a stable manifold on the saddle point here, the actual trajectories will go off like this on both sides. So the future is very different, even though the initial condition is very close. Now what's happening is, in this interval under this evolution, every rational point on this line is acting like a separatrix. It's throwing away the irrational points on either side of it, both sides. And how rapidly are those fellows diverging? I put it to you that it's diverging exponentially in spite of this modulus, because of the following fact. I want to know how fast xn is moving away given a certain x naught. So I want to know what's the modulus of f n iterate of x naught minus, or x naught plus epsilon, since you're familiar with adding the increment on the left, minus f n of x naught. How fast is this separation happening? This modulus for a given separation. In the limit in which epsilon goes to 0, and these points are arbitrarily close to each other, as n tends to infinity. I expect this fellow to go like 2 to the power n. As you can see, this is 2 to the n x naught and 2 to the n x naught plus epsilon. So there's a 2 to the power n. I want to extract that 2. So it's going like e to the n log 2. I want to extract that log 2. How would you do that? You take logs. So take log. After n iterations, it goes like n log 2, right? I want the log 2 part, so I divide by n. And I now must take the limit in which n goes to infinity and epsilon goes to 0. So, what should I write here? I want to write a limit here. There are two limits to be taken. One of them is n tends to infinity, epsilon tends to 0. Which order should I take these limits in? Well, in mathematics, the limit of a to the power b, as a goes to 0 from the positive side, b goes to 0 from the positive side, depends on which one you take first. In one case you get 0, in one case you get 1. And mathematics is well defined for both of them. Only the physics can tell you which is the right answer. So that's where physical input is needed. Just like in disordered systems, when you take thermodynamic averaging, thermal averaging, and configuration averaging, if you do it in the wrong order, you get nothing. But you do it in the right order, you do thermal averaging first and then the averaging over configurations, you get non-trivial answers. Right? In some sense, because the thermal variables are very fast and the quench variables are essentially static. So, or you assume some self-averaging problem. In exactly the same way, you want to know what's the separation of points at a given point. So you'd like to take the limit epsilon goes to 0 first, and then over long times. So this is epsilon goes to 0, n tends to 0. If you did it the other way, you get 0, which is a trivial answer, because this can never be bigger than 1. After all, that's the size of the interval. So these 2 points can at best be as far separated as the system size of the interval, which is 1. But there's a 1 over n. And this will let you go to 0. But the moment you do it in the other order, you may get a non-zero answer at the point x naught. This will be equal to the exponential rate of separation of trajectories referring to the point x naught. So this will be a function of x naught. It's called the Lyapunov exponent at x naught. Actually, it's not at x naught itself. It's at the entire orbit of x naught. Because it's n going to infinity, You would have started with x1 or x2 corresponding to this x0 and you would not get any difference at all.
Or it corresponds to average separation.
Pardon me?
Corresponds to average separation.
Corresponds to?
Average separation.
Average separation. Average exponential rate of separation on the orbit of the point x0. It's the average exponential separation over all the points. Suppose this is x0, that's x1, this is x2, that's x3, this is x4, and so on. All these points are being sampled by this guy. So it's the average exponential separation of the orbit of this initial point x0. And the idea will be that this will become independent of x0. Wherever you are, this will be the same. Not always true, but in this case, yes. So, main thing I want to emphasize is you must appreciate the fact that this limit is taken in a specific order. It's not in the wrong order. Then, if it's a bounded phase space, as is in this case, then this number can never be bigger than the size of the phase space. And then this 1 over n will just give you 0. So you really want to find out at the point x0. So you want the limit as epsilon goes to 0 first and then long time. Then, but what does that tell you? What's this equal to? Because now we have a very simple formula based on calculus. This is equal to, by definition, limit n tends to infinity, 1 over n log the derivative dfn of x over dx modulus at the point x equal to x. Isn't it? By definition. This is some function of x0. It's not plus epsilon minus this divided by epsilon modulus. Take limit epsilon goes to 0. Pardon me? I don't care. I don't care. But now, when I differentiate and write continuous differential, etc., I'm assuming there is a measure, there's a dx and so on. If I take x0 to be at a fixed point, then there will be no separation at all. Things will fall in automatically. So therefore, except for sets of measure 0, everywhere else on the interval, this will be valid automatically. We will see this explicitly in examples, because I'm going to look at cases where you have a map, but there is a fixed point, stable fixed point, and then you will discover that the Lyapunov exponent it has to be 0. In fact, it will turn out to be negative, because everything will have to fall into that point, and instead of exponential separation, you have exponential contraction. We'll have to check that out. But do you agree that this has become a formula now? But we can go further. This is equal to limit n tends to infinity 1 over n log of dfn of x, that's xn, but xn is f of xn minus 1. I differentiate with respect to xn minus 1 times d f xn minus 2, because that's dxn minus 1, both sides, over dxn minus 2, dot dot dot, all the way up to df x0 over dx at the point 1. I've used Lewis notation. By this I mean the derivative of this function at the point x0. Modulus. So that's log of a product. So this is equal to limit n tends to infinity 1 over n summation from I equal to 0 to n minus 1 log f prime xi over this orbit. Now what's it in the map that we looked at? What's it for the Bernoulli map? This is a general definition. What is it for the Bernoulli map? In that case, no matter where xi was, the slope of the map was equal to 2. Always. So, except at the discontinuity. But everywhere, from the left and right, the slopes are still 2. And in an infinite sum like this, those terms, any finite number of terms drop out in any case. So what does it do? What's this equal to? This log 2 comes out and this summation gives you n and that cancels this n and the answer is log 2, which is greater than 0. So you have a finite positive Lyapunov exponent. This is exactly telling you very precisely that there is an exponential separation of trajectories, and this also tells you how it's possible to have such an exponential separation even though the phase space is bounded, because in this specific way of taking limits. And whenever you have at least one positive Lyapunov exponent in a dynamical system, you say it's chaotic. And now there's no unique definition of chaos in a rigorous mathematical sense, but let me write down the accepted operational definition. Chaos if 1, you have bounded phase space, 2, exponential sensitivity, this is called exponential sensitivity to initial conditions in at least one direction at phase space. And 3, no one has proved this, but it's believed that it's true because there are no exceptions have been found. Dense set of unstable period. You seem to need this, because that's the mechanism by which you have this separation happening. And we have that satisfied in our case, because all rational numbers fall on unstable periodic orbits. They form a dense set in the unit interval. Now, of course, this was a very simple model because all the slopes were constant.
So these three informations exist in the Lyapunov exponent.
Pardon me?
These three informations exist in the Lyapunov exponent.
Well, the Lyapunov exponent doesn't, it implies all these three guys, but then it becomes positive. But the fact is that,
That's why it is necessary and sufficient condition.
Well,
At least
it's not, I would say this is a sufficient condition. This is a sufficient condition. But no one has proved this rigorously. No one has proved that condition number 3 is necessary. No one has proved this rigorously. In model systems, yes. You can see what happens when we remove this condition, etc., etc. But in generality, no. And this definition of chaos is an operational definition. It is not necessarily the only one, but it's the most convenient one for all practical purposes. And every chaotic system that we know about, where there's a positive Lyapunov exponent, you can detect this. This is also present.
So lambda can be negative also.
Now then I won't call it chaos. Then I won't call it chaos. In fact, let's do that. Suppose you got a fixed point, which is stable, towards which things go. Then, good point. Let's just look at this formula and ask what's the Lyapunov exponent corresponding to any point which falls into this fixed point. What will it be? What will it be? Because after a sufficient number of iterations, this xi will be arbitrarily close to this fixed point. Right? So in the limit, when n goes to infinity, you just have a whole lot of log f prime at the fixed point, x stars. So for a fixed point, stable fixed point, for example, this lambda will be equal to, so this sum will be dominated by an infinite number of terms, for each of which this quantity is a constant. It's log modulus of the slope at the fixed point. So it will simply go, and the 1 over n will cancel with the summation, and you get log f prime of x. But this number is known to be less than 1 for a stable fixed point. So the so-called Lyapunov exponent will not be a positive number, but a negative number in set cases. And there is no exponential separation. What if it's a period 2 cycle? such that A goes to B, B goes to A, then you see for a period 2 cycle, that product is less than 1 second. So again, it's not going to be a positive Lyapunov exponent. This product magnitude is less than 1. So whenever you have a stable attractor, there's no Lyapunov exponent, which is positive. It's only when all the period cycles have become unstable, then you start having chaos. Now you could ask the more interesting question. Suppose I change some parameter in the dynamics. Is it possible that the system starts, goes to a stable point, periodic stable fixed point, then it goes to some other fixed point or periodic orbit,